Welcome to qnawire.
Here we have a non-ideal gas steam binary system. Let's see here. We are down here at, this is, let's see here. Power at so air comes in here, goes through the compressor, goes through the combustion chamber, goes through a gas turbine, and then goes out through a heat exchanger. And then we have a cycle here of steam where condensed from the steam turbine goes through a pump, goes into the heat exchanger, gets boiled from the hot gases coming out of this gas turbine, goes into the steam turbine, and then get some work out, and then we send it on to the condenser to get cooled off. Well, not cooled off, but to get condensed to a saturated liquid, so we get some energy, we dump energy out of it. So this is what we look like here in the TS diagram. So we have 5 to 6 to 7 to 8 to, I guess I didn't put that down here. That should be 9 here. Maybe not do it in blue. 9, 9. And then really we don't have anything here. We're just dumping it out into the atmosphere at 9. And then our normal non-ideal Rankine cycle. So again, we have, you know, these aren't vertical lines. We're told that the efficiency of the compressor is 90%, and the efficiency of the gas turbine is also 90%. The efficiency of the steam turbine is 95%. The temperature of the steam entering the turbine is 600 degrees C. We're told they use the efficiency of 1 for the pump. Again, we probably don't even really need to include the pump power. We're in English units here, so this is 800 psia. What did we have the, let's see here. Oh, did I say degrees C? This is degrees Fahrenheit. Pressure, the steam condenser pressure is 5 psia. Oh, I did write it in there. That's what this 5 is here. What else is there to say about this? I don't think any. Oh, here we have atmospheric conditions of coming in here, and then up here at 6 after out of the combustion chamber, or 7 out of the combustion chamber, we're at 25,000, 2,560 Rankine going into the gas turbine. Okay, so let's see here. We can start our analysis then. So which is kind of lengthy, but we'll do it anyway. So on the gas side of things, we have we'll just use ideal gas isentropic expansion or isentropic compression across the compressor. So we can get T6 prime, and that's 1043 Rankine, which again from using the efficiency of the compressor, we find that the actual temperature coming out of the compressor is 1099 Rankine. So then we have isentropic expansion through the turbine. So we know T7, and we can find T8 prime, and that winds up being 1326 Rankine. And then knowing the efficiency of the turbine, we can get T8, the actual temperature there, which is 1449 Rankine. And I should put a Rankine here because I'm assuming that if there's no units that it's degrees Fahrenheit. Now we're told that let's see here, we're told that the gas leaves the heat exchanger 50 degrees Fahrenheit hotter than the saturation temperature of the steam in the heat exchanger. Okay, so the steam in the heat exchanger is at 800 psia. Is that right? Yeah. And so we can figure out the saturation temperature, and it's 50 Rankine or 50 degree. We can add 50 Rankine because again, we can figure this out in Rankine, and then we can figure out this. what the temperature is coming out. So the saturation temperature, we can get that in Rankine, and then add 50 Rankine to it, which is the same as adding 50 degrees Fahrenheit. Again, so because we're adding these, we can change the units here. And that winds up being 1028. 1028 Rankine. Now, let's see here. We have, now we move on to the steam side. Enthalpy at the pump inlet, specific volume, work into the pump, specific volume, enthalpy out of the pump. Pressure and temperature into the turbine, enthalpy into the turbine, entropy into the turbine. And then we can look at the isentropic case at 4 and get the isentropic enthalpy at 4, and then use the efficiency to get the actual enthalpy at 4. Now we can have a, let's see here. So that's 4, and now we can get the net work out of the gas turbine using constant heat capacities for the air that we can look up. And again, we have this is the work out of the turbine and the work into the compressor. And so that winds up being the specific work out of the gas side winds up being 132.5 kilojoules per kilogram. Now, the net work out of the steam side, the specific network anyway, is the work out of the turbine, which is this, the steam turbine, minus the work into the pump, which is 341.8 kilojoules per kilogram. Now, an energy balance on the heat exchanger. This is the change in enthalpy of this gas. This is change in enthalpy of the steam. And so we can get this ratio of the mass flow rate of the, this is the flow of, change in the flow, yeah. So we can get the mass flow rate of the gas divided by the mass flow rate of the steam. And that winds up being about, what is that, 8.876%. So we have the gas flow is much smaller than the steam flow. Is that right? Let me check here. I suspect, let's see here. Did I write that wrong? Oh no, man. So why? Yeah, I did write that wrong. Because usually we have a lot more mass of air going through here. Let me just erase all that. So that is actually, this is m dot steam divided by m dot gas. There we go. And we can now use that number to get the heat transfer in per mass flow of gas, or of what did I do? Okay, yeah. But this is 1. We're trying to get everything on a kilogram of gas flow basis. So we don't really need to change anything here, but we can I just showed this here to show that, we have to make sure we're on a kilograms of air basis here, or kilograms of gas. So this is the specific heat into the combustion chamber. And then the specific heat out of the system, we have the, let's see here, we have the specific heat 9 and, let's see here, 9 and 5. So 5 is here, 9 is here. So that is the, is that right? Yeah. So that is the That's the heat that we're losing. We're basically the heat that we're dumping to the atmosphere, because 5 is atmospheric, and this is the temperature coming out of the heat exchanger. So this is the heat out, kind of like you can think of it as a condenser after the heat exchanger, right? And that's already on a mass, on a per kilogram of air basis or kilogram of gas basis. And then this is the enthalpy, this is the heat out of the condenser. But remember, we're getting on a kilogram of gas basis, so we need to multiply by this factor, this ratio here. Again, we could think about this as multiplying everything through by m dot g, and this is, power out per kilogram of gas. So total power out, and then divide through by m dot g. Now, so this is so again, now we're on a kilogram of air basis here by using this factor here. It's basically a unit conversion. And we wind up with 187.8 kilojoules per kilogram of air. So this is kilojoules per kilogram of air also. And so now that we have these things basically have the same units, then we can get an efficiency out of there. So it's 1 minus this divided by this. And it turns out that that is 46.43%.